This is Algebra Lesson 4-2, Patterns and Linear Functions. There are several vocabulary words here that are very critical to understanding this lesson and every lesson that comes after it in this chapter. So it's very important that you write these words down and make sure that if I write down any examples, you copy them. A dependent variable is a variable that depends upon the value of another variable. It changes in response to another variable. For example, if I sell magazine subscriptions and I earn money, the amount of money I earn depends completely upon the number of magazine subscriptions I sell. The more magazine subscriptions I sell, the more money I earn. Independent variable. This variable can stand all by itself. It does not depend upon anything else. Okay? The number of magazine subscriptions I sell does not depend upon anything. I mean, it may depend upon me actually going out and selling some, but it doesn't depend upon how much money I earn. Okay? The money I earn depends upon the number of magazine subscriptions I sell. The dependent variable is often considered to be your y variable, and your independent variable is always often considered to be your x variable. The input is the value of your independent variable, otherwise known as x. The output is the value of your dependent variable, otherwise known as y. A function is a relationship that pairs each input value with exactly one output value. Okay, and this is important because there will be things that there's a difference between what we call a relation and a function, which we will talk about in a couple of lessons, if not the next lesson. So it's kind of important to understand that a function relation is a relationship that pairs one input value with exactly one output value. Okay, so in magazine subscriptions, I earn a different amount of money if I sell 10 subscriptions than I do if I sell 20 subscriptions. Okay, a linear function is a function whose graph is a non-vertical line or part of a non-vertical line. Okay, a function would look something like this. If I had a graph, here's my x and y axis. If I had a graph, if it looks like this, that's a function. Okay, also what would be a function is if something looked like this. That would be a function, even though it's a curve and it's not a straight line. It's a part of a line. Alrighty. The value of one variable may be uniquely determined by the value of another variable. Such relationships may be represented using a table, an equation, a set of ordered pairs, or a graph. And today we're going to learn how to do all four of those, maybe all four of them within the same problem. But nonetheless, it is important to be able to figure these out. Okay, so we're going to talk about how you can look at something and describe the relationship using a table, an equation, an ordered pair, or a graph. So let's take a look at a geometric relationship. In this diagram below, it says, what is the relationship between the figure number and the number of squares in the figure, and how can it be represented? So let's take a look at this. If I look at the figure number, okay, if I put down here figure number and then number of squares. Now I'm going to make a little table here. In the first figure, I have 4 squares. No, 5 squares. 1, 2, 3, 4, 5. So I have 5 squares. In the second figure, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 squares. In the third figure, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 squares. So we've shown a table, but we want to know what relationship. The table shows us the numbers, but it's not really good at showing us the relationship. Okay, like I said before, we can think of these things as being like x and y. If I let my figure number be x and my number of squares be y, I'm going to find a relationship between the number of squares and the figure number. So the first thing I'm going to do is I'm going to look at the number of squares. Do they constantly go up by the same number? So if I look at this from 5 to 9, that goes up by 4. From 9 to 13, that goes up by 4. It's implying that there's a relationship there, isn't it? Since I know that they're constantly, each one of the figures, each figure is jumping up by 4 squares, I'm going to take my figure number, I'm going to multiply it by 4. So 1 times 4 is 4, 2 times 4 is 8, 3 times 4 is 12. And now I'm going to see, is there a relationship between my new figure number in blue, and the number of squares in green. So from 4 to 5, we add 1. From 8 to 9, we add 1. And from 12 to 13, we add 1. So I've found a relationship. My number of squares, y, is equal to my figure number multiplied by 4, so 4x, and then added by 1. So what's really nice about this is if I wanted to know how many squares am I going to have in the 9th figure, I could simply replace x with 9. I could say in the 9th figure, y would equal 4 times 9 plus 1. 9 times 4 is 36, plus 1 is 37, so there should be 37 squares in the 9th figure. And I didn't have to draw figure 4, 5, 6, 7, 8, and 9 to get there. I mean, I could have, but it was so much easier to represent it using what we call here an equation. Okay, so that's one way of doing things. We can write a table, and from that table, we can get a relationship between the numbers, which would give us the equation. Let's look at a linear function. It says, is the relationship in the table at the right a linear function? Describe the relationship in words with an equation and a graph. Okay, so the first thing we're going to do is we're going to see if this is a linear function by graphing these values. So when x is 0, y is 8. So I'll go 0 on my x-axis, and I'll go up to 8 on my y-axis, and I'll plot that point. When x is 1, y is 10. So go over to the x-axis, go over 1, and up 10, and plot that point. When x is 2, y is 12. So on the x-axis, I'm going to go to 2. On the y-axis, I'm going to go up to 12, and I'm going to plot that point. And last but not least, 3, 14. So on my x-axis, I'll go over 3. My y-axis, I'll go up for 14. That definitely looks linear to me. It looks like it's going to in a straight line. So is it a linear function? I believe it's a linear function, because it looks like I could connect those dots. I'm not going to, because I don't know what they represent at the moment. They could represent how many books you read each week. Okay, and you can't read parts. You could read parts of a book, or how many books you sell, but you can't sell part of a book. You have to sell a whole book. You can't say, oh, I'm going to sell you 2 chapters of this book, rip out the 2 chapters of the book and sell it to somebody. It's actually illegal to rip up a book like that and sell it. All right, so we know it's linear. So let's look and see if we can figure out an equation for this, because if we can figure out the equation, I think we could explain in words what this function says, because once you can explain it in linearly, that would be good. So I'm going to look at, now this table happens to be done vertically versus horizontally. The last table we did was horizontally. This table is vertically. So I'm going to look at the difference between my y values. From 8 to 10, we add 2. From 10 to 12, we add 2. From 12 to 14, we add 2. Since we have a constant difference between each one of those numbers, I'm not going to take my input column and I'm going to multiply it by 2. So 0 times 2 is 0. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. Now I'm going to look and say, is there a relationship between this 6 and the 14? If I look at that, well, 6 to 14 adds 8. How about from 4 to 12? 4 to 12 adds 8. How about 2 to 10? That adds 8. From 0 to 8 also adds 8. So I've found the relationship here. I know my output, y, is found by taking my input x, multiplying it by 2, and then adding 8 to it. So I know this is a linear function. I've described the relationship with an equation. Here's my equation. I've described it with my graph. There's my graph. Now I need to describe it in words, kind of like what I just said. My output is found by multiplying my input by 2 and then increasing it by 8. So the output is found by multiplying the input by 2 and then adding 8. You can say increasing or adding is fine. So there, we described the function using words, using an equation, and using a graph. Now let's look at a set of ordered pairs. Does the set of ordered pairs 0, 2, that's supposed to be a comma there, 1, 4, 3, 5, and 1, 8 represent a linear function? Explain. Well, let's find out. Let's graph these. 0, 2. So remember, on an x and y coordinate plane, this is your x-axis, this is your y-axis. You should always label them. Always graph x before y. X comes first in the alphabet, alphabetically. So we'll graph x before y. So we start at the origin, which is where the two axes cross. It says to go left and right 0 and up 2. So I go left and right 0, up 2. That's my first point. There's 0, 2. Then I'm going to start back at the origin. 1, 4 means go right 1 and up 4. So there's my second one. So far it looks linear. Let's graph the third point. The next one is 3, 5. So start at the origin, go over 3, 1, 2, 3. Go up 5, 1, 2, 3, 4, 5. Still looks linear, doesn't it? And last but not least, let's graph 1, 8. Start at the origin, go over 1 and up 8. Well, so far it was linear until we got to that last point. As soon as we added that last point, all 4 of those points cannot be on the same line. 3 of the 4 could, 2 of the 4 could, 1 of the 4 could, but I have to get all 4 on the same line. All 4 of them cannot land on the same line, so no. Okay, it is not a linear function. Okay. And the reason it is not a linear function is because we have 2 output values for the same input value of it, 1. Okay. Because the input value of 1 has 2 different output values. Oh, I can't spell. Let's spell that properly. 2 different output values. So you can look at something, you can graph it. Once you've graphed it, you can look at it and say, hey, can I draw one straight line that will go through all of these points? No, I cannot. And if I cannot, then it is not a linear function. All right, closure question for today. What are the ways to represent a relationship between an independent and a dependent variable? I've already talked about this. We've actually practiced it. So what are the ways to represent a relationship between an independent and dependent variable?